Gravitational waves are essentially ripples in the fabric of space-time. Albert Einstein actually predicted the existence of gravitational waves back in 1916 with his general theory of relativity. Einstein predicted that massive accelerating objects disturb space-time kinda like the waves seen when throwing a rock into water. These ripples would travel at light speed through the universe and carry with them information about how they originated. Actual proof of the existence of gravitational waves was not discovered until 1974, when astronomers in Puerto Rico discovered a binary pulsar from two very dense and heavy stars in orbit around each other. This was exactly what was predicted by Einstein's theory of general relativity. Astronomers then began measuring the period of the star's orbit to see how it changed over time. They eventually determined that the stars were getting closer to each other at the exact rate predicted by Einstein. We've been monitoring these changes for over 40 years, and the data continues to agree so precisely with general relativity. Ever since the discovery of the binary pulsar, astronomers have been studying the timing of pulsar radio emissions, and they found similar data which again further confirmed the existence of gravitational waves. However, all the evidence for the existence of gravitational waves were obtained indirectly or by calculations. There was still no physical evidence of gravitational waves. But that all changed on September 14th of 2015, when evidence of the distortion in spacetime from two colliding black holes was physically sensed at Ligo.
Ladies and gentlemen, we have detected gravitational waves. We did it.
LIGO is the world's largest gravitational wave observatory. LIGO consists of two laser interferometers thousands of kilometers apart. Two laser interferometers are needed to detect gravitational waves because they are extremely sensitive to the smallest vibrations. Scientists need to be able to distinguish gravitational waves which occur at the same time anywhere on Earth, to local vibrations like those from earthquakes or from trucks driving on roads at a specific location. This allows scientists to ignore waves measured by only one interferometer. But what are interferometers? They're called interferometers since they merge sources of light to create an interference pattern that's measured and then analyzed. These interference patterns are what contain valuable information that can usually not be measured and analyzed in any other way. LIGO is so powerful that it's able to measure a change in the interference pattern 1/10,000th the width of a proton. The way an interferometer works is by first passing a laser beam through a mirror that splits the beam into two identical beams, where one passes straight through and the other is reflected 90 degrees. The beams travel down the respective arms of the interferometer, and once they reach the end, a mirror reflects each of the beams back towards the first mirror. Once the beams reach the first mirror, they merge back to a single beam. When the beams merge, the waves from the laser constructively or destructively interfere, before reaching a detector which measures the beam's brightness. The arms of the interferometer are exactly the same length. Therefore, the distance traveled by both beams are the same. That being said, depending on the way the mirrors are positioned, the detector will see a brighter beam than the split beams due to constructive interference, or no beam at all due to destructive interference. At LIGO, they've set the mirrors in a way that no beam reaches the photodetector when the arms are the same length. If the photodetector measures light, one arm is longer than the other, and one beam traveled the longer distance, and therefore takes longer to reach the first mirror to merge with the other. That means the phases of the waves will be offset when they merge and cause an interference pattern. Any change in the beam's intensity means that an event occurred to change the distance traveled by one or both of the beams. That event is space-time stretching in one direction and squeezing in the perpendicular direction. The detection of gravitational waves by LIGO originate from the largest energy-releasing events in the universe, like exploding stars, colliding black holes, and the Big Bang. Now that we're able to observe the universe in a way we never could before, we have the ability to get a better understanding of the nature, dynamics, and structure of these huge events in our universe. The goal now that gravitational waves have been detected is to have a network of detectors like Ligo around the world that can quickly determine the exact location of the source of the gravitational waves. Astronomers could then immediately start looking for sources of these waves. The impact of Ligo goes way beyond developments in physics, astrophysics, and astronomy. The multiple designs and ways to build these detectors have in fact benefited many other fields like optics, materials science, cryogenics, geology, and space science.